Okay, today we can start our ninth lecture on hydraulic machines. So we are discussing our first module, and in the first module we are discussing the impact of jet on a stationary plates. And we have already discussed our cases such as force exerted by a jet on a stationary vertical plate and the stationary inclined plate. And there's a third case also, and that one is the stationary plate, which one is curved one. Okay, so today we are discussing the force exerted by the jet of water, that is the impact of jet on a stationary curved plate. That is our topic. The force exerted by a jet of water on a stationary curved plate. Let's have a look. So this is the diagrammatic representation or the velocity profile of the force exerted by a jet. So here is a pipe, and at the end of the pipe there is a nozzle is connected and water is coming out of the nozzle, and there is a, you can see that this one is the curved plate which is fixed at the both ends. So it's a fixed curved plate, and the force, and we have to find out the force exerted by this jet of water coming out, and it is tracking here and it is coming out through this way and with the inclined angle. Since it is a curved plate, the jet will be coming out at an inclined angle, that is angle theta. So this is a case one is the jet strikes the curved plate at the center. There are two cases with that. First one is the jet is striking the plate at the center. So here. And the second case is the jet is striking this edge. Okay, this bottom end. The jet is coming through this edge and striking here and coming out through this way. But in this case, that is case one, the jet is coming and coming out of the nozzle and striking at the center of the curved plate and coming out through this way. So let's analyze these things. So before get into the derivation, these are our assumptions. That is, the plate is smooth. So if the plate is smooth, there won't be any loss of energy due to the impact. Assume there is no loss of energy due to the impact of jet in the tangential direction. And the velocity of the outlet of the plate can be resolved into two components. So here you can see that when water is coming out or the jet is coming out with a velocity v, and it is making an angle theta with the horizontal. So we can resolve this outlet velocity component into two. That is a vertical component and this one is a horizontal component. Let theta be the angle made. Okay. And v is the velocity. Then v sine theta will be the vertical component and v cos theta is the horizontal component. And these are all we studied in your how to resolve these forces. It's all you studied in your mechanics lesson something. Okay, so and in your previous lesson also lecture also we have described elaborated how to resolve these forces. So if you have any doubts again you can contact me and I can clear it personally. Okay. Okay, let's move to the next section. That is first one, that is we have to resolve these forces into two components. That is first one is the in the direction of jet, that is in the horizontal direction. The force is resolved in the horizontal direction, and second is the perpendicular to the direction of the jet, that is in the y direction. So the first case is the force exerted by the jet in the horizontal direction, and the case one is the jet of water is striking the center of the curved plate. So this one is a curved plate and this is the center, and the jet is striking at the center and then coming out through this way and coming out with a velocity v, and it is inclined at an angle theta. So the jet is coming out with the same velocity since the curved plate is smooth. So we are assuming that the plate is smooth. So it is smooth means there is no loss of energy. So initial velocity is equal to final velocity. So that is striking with the velocity v and coming out with a velocity v. But there is an angle of inclination in the horizon, that is theta. So here we have to find out the component of force in the direction of it, that is in the direction of it, that is a horizontal direction. So jet is going in the direction x. So we have to find out the force in x direction. So the same steps that we are employed in the previous derivations. So you should remind that almost all this derivation in this module are same. Only the diagram is changing and the velocity components are changing. the striking direction. Only direction is changing, and first case the vertical plane, in second case the inclined plane, and third one is the curved plane. This is the only difference. Only the angle of inclination changing is the, and remaining things are same. Only you need to apply your logic. Then you can simply derive these expressions. All the terms are same. Okay. So the Fs will be equal to, we can say it is a rate of change of momentum. Then Fs is equal to change of momentum in this direction. Then Fs is equal to mass into initial velocity minus mass into final velocity. That is initial momentum minus final momentum. Then mass is taken out. Then divided by time. That is the mass flow rate. That is rho into A into V. That is mass per second into initial velocity minus final velocity. So that's what we written here. That is mass per second into initial velocity in the direction of jet minus final velocity in the direction of jet. So here Fx is to be calculated. So that is in the direction of jet. The force is to be find out in the direction of jet. So we have to take the velocity also should be taken in the direction of jet. That is mass per second multiplied by initial velocity in the direction of jet minus final velocity in the direction of jet. Then mass per second into, let us assume that v1x is the velocity in the direction of jet and v2x be the velocity in the final velocity in the direction of jet. Then mass per second is rho into v, a into v. So into initial velocity in the direction of jet. This is the initial velocity. Okay, v is the initial value in the direction, means this is the x direction. What is the velocity in the x direction? Before striking, what is the velocity? V. Before striking, its velocity is v. So it is v. And after striking, what will be the velocity in x direction? So just strike, then after striking, the jet is coming out through this way at making an angle theta. So if you resolve this velocity due to component, then horizontal component will be v cos theta. So here you can see that it is moving in the reverse direction. So it's a negative direction. So we have minus v cos theta will be the horizontal component after striking. That is the velocity of jet after striking in the direction of the jet. It is velocity component in the direction of jet after strike. First one is velocity of jet in the direction of jet before striking, and next one is after striking. So before striking it is v, and after striking is v cos theta. That is minus v cos theta. Then we have rho a v into v minus v cos theta. Minus of minus plus. Then it will be equal to rho a v into v minus minus of v cos theta. That is rho a v into v plus v cos theta. V is a common term here, so we can take it out, and it is equal to rho a v square into 1 plus cos theta. This is the expression for force exerted by the jet of water in a stationary curved plate in the x direction. Okay. Similarly, next we have to find out the force exerted by the jet in the y direction, that is the perpendicular to the jet. And here also we are following the same steps that we are employed in the previous cases, that is in the horizontal direction. So the velocity should be taken out in the perpendicular direction, that is mass per second into initial velocity of the jet in the direction perpendicular to the jet. So the velocity of jet in the perpendicular direction before striking. What is the perpendicular direction velocity? It's evident from here that it is 0. There is no perpendicular velocity. There is no velocity in the perpendicular direction before striking the jet. And jet is striking here, and it is coming out through this way, and then a velocity v, and it is making an angle theta with the horizontal. And if we resolve this component into the vertical direction, we will get the v sin theta. And this v sin theta is the velocity of jet after striking in the vertical direction. That is equal to v sin theta. So here minus v2 as the y, that is v sin theta. Then it will be equal to rho a v into 0 minus v sin theta. Which on simplification we will get, which is equal to minus rho a v square sin theta. This is the expression for the force exerted by jet in the vertical direction. So the force exerted by the jet in the vertical direction in the case of a stationary curved plate is equal to minus rho a v square sin theta, and similarly the force exerted in the horizontal direction is equal to rho a v square 1 plus cos theta. Okay, that's for today. Thank you for watching.